Oftentimes, students are confused about when they can distribute exponents and when they can't. To give you an example, let's take a look at a plus b squared, a plus b to the 1/2, and ab squared. I see a lot of students who do this. They say that's the same thing as a squared plus b squared. And I see even more students do this. They distribute the 1/2. They distribute the square. Well, ab squared is just ab times ab. Reordering, it looks like I have a squared times b squared. So it looks like this was a legitimate operation. I proved it. So the question is this a legitimate operation? And I'd like to convince you that in general, neither of these guys is true. And I'm going to do it using two different devices. So to recap, I just showed you that when we're multiplying, and the same thing holds for dividing, you can distribute the exponents. When we're adding, I want to convince you that you can't, in general, distribute the exponents. So let's see why this first one isn't true, and I'm going to show you why it's not true with a picture. Well, a plus b squared relates to the following diagram. What is a plus b squared? A plus b squared is just this length times this length. In other words, it's the area of the square with sides a plus b. Okay, so it's that whole area. A squared on my picture is just this box. B squared on my picture, let's see, B, is just this box. Same area? No. In fact, the only way for them to have the same area is if AB, let's see, AB plus AB, the only way for them to have the same area is if that quantity happens to be 0. Okay, so in general, this is not true. I'm going to convince you that a plus b, actually let's put a little question mark up here. Try to convince you that in general, a plus b to the 1/2 isn't equal to a to the 1/2 plus b to the 1/2. In general. Sometimes it's true. In fact, if a equals 0 and b equals 0, that is true. 0 plus 0 is 0. The square root of 0 is just 0. The square root of 0 is 0. The square root of 0 is 0. So we have 0 equals 0. That works. But what about in general? Well, to show that it's not true in general, I'm going to just come up with a numerical counterexample. And I'm going to use some numbers that are easy for me to deal with. So what do I mean easy to deal with? I'm going to be able to take their square roots. So let's let a equal 4 and b equal 1. The left-hand side becomes 4 plus 1 to the 1/2. The right-hand side becomes 4 to the 1/2 plus 1 to the 1/2. 4 to the 1/2 is the square root of 4, aka 2. 1 to the 1/2 is the square root of 1, aka 1. Is 3 equal to the square root of 5? Not today, it isn't. So that's why that's not true in general.